So now let's consider our harmonic motion problem, where we have a mass vibrating on a spring. There's a constant k, which is determined by the spring, how strong or weak it is, and a constant a determined by the object's shape and air resistance, and then the mass of the object m, and then some external force that's possibly changing over time, called f of t. So what do? We plug everything into our Laplace transform and we use linearity. And what happens? The Laplace transform of a constant times the derivative is just a constant times the Laplace transform of that second derivative. And we have a formula for the Laplace transform of an nth derivative. So n is 2 in this case. So that first term is just going to become m times s squared times the Laplace transform of our solution x, which I'm calling capital X. So capital X is the Laplace transform of lowercase x. And then I subtract s to the first power times x of 0. And then I subtract s to the 0 power, which is 1, times x prime of 0. And then I use that formula again for the second term. A is a constant, it factors out. I get s to the first power, because it's the first derivative, times the Laplace transform, and then minus s to the 0 times x of 0, lowercase x of 0. And the last term is just a constant times x, so I get a constant k times the Laplace transform. And the right-hand side is just the Laplace transform of lowercase f of t. Regrouping things. Notice the only thing we don't know here is the capital X of s. That's the only thing. Everything else is given to us. S is a variable, but everything else is given to us. M, A, and K is known. X of 0 will be known. X prime of 0 will be known. Because this is a second order problem, we're going to have initial conditions that are given to us. And the function little f of t is given. So let's just solve this for x, capital X of s. So just doing the algebra, all you're really doing is adding these two terms to the right side and then dividing by this quadratic expression. And since this is the Laplace transform of lowercase x of t, we just plug the right-hand side of this equation into the inverse Laplace transform, and we know that that's what x of t is. It's the inverse Laplace transform of all that stuff, which is equal to capital X of s. So basically, I've just solved every single initial value problem, which is a second-order linear equation with constant coefficients. So there's a formula. If you wanted to derive a formula for first order or third order or 500th order, you could do it in a similar manner using these formulas related to the Laplace transform, and you'd always be able to solve it for capital X of s, and then you just know that x is just going to be, x of t is going to be inverse Laplace transform of that. So here's our initial value problem. We just determined what the solution is. Again, I put x sub 0 for the actual value of x of 0, and I put v sub 0 as the actual value of x prime of 0. So there's our solution. We just have to determine what capital F of s is and plug in all the numbers that were given. So plugging in the numbers, determining the Laplace transform of our right-hand side, and then we just have to compute this inverse Laplace transform to determine our solution x of t. So let's look at a simple example. So here's our second order initial value problem. Go straight to our formula. X of t is this stuff, but what is this stuff? F of s is the Laplace transform of t, the right-hand side function. We know what that is. It's 1 over s squared from our power function formula. M is 1 in this case, A is 0 in this case, and K is 1 in this case. And then our x of 0 is given to us as 0, and our x prime of 0 is given to us as 1. So we just plug all that stuff in. Notice this is the capital F of s, so I'm going to just algebraically rewrite this so they don't have negative exponents for the powers of s. And then at this point, we just use linearity and split it up. And this isn't the greatest form, so we factor things and simplify things if we can. And then what do we notice? We notice that we have two inverse Laplace transforms that we have to figure out. This one on the second term, that's a direct application of our formula for the sine function. So this is just sine of t, because the Laplace transform of sine of t is this 1 over s squared plus 1. Again, if those 1's were a 5, it would be sine of 5t. For this first term, though, we have a product of two functions that are simpler. 1 over s squared times 1 over s squared plus 1. So this is where we could use our convolution formula, like we did when we discussed how to compute inverse Laplace transform. We had to compute a convolution. We could do that here, but you can also use another method, which I want to show you, which is called the method of partial fractions, to rewrite this product as a sum of simpler things, or difference. Okay, it's really just a way of, when you learn algebra, you learn how to combine like terms to put fractions together. It's just how do you break it apart again, so it's not simplified that way. Again, I'm not going to go over that method. You can use it. The problems that I'm going to give you aren't going to be super complicated, so just computing the convolution integral will be good enough. But if you want to do it algebraically, feel free to. So there's our model again. We've used our formula for the solution, and then we've split this into two different inverse Laplace transforms. The one on the left, we're going to not use the convolution this time. We're going to use an algebraic observation. Just realize that the stuff in the first term can be written as a difference of two simpler things that are easier to determine the inverse Laplace transform of. The inverse Laplace transform of 1 over s squared is t, and the inverse Laplace transform of 1 over s squared plus 1 is sine t, but I actually don't even care, because once I split that up, this negative 1 over s squared plus 1 is going to cancel with the positive 1 over s squared plus 1 from here. So all we're going to be left with is this, and we know that's t. And if you look at x of t equals t, you can easily confirm that it satisfies our differential equation and initial conditions. Again, this was a very easy example that other method like undetermined coefficients could have easily solved. I just wanted to illustrate an example of how we actually use our formula that we've derived. This is not in your book. I just derived it for our use for second order equations, and how to go about computing these inverse Laplace transforms.